Welcome to this review for the grade 9 science class in Ontario with the course code SNC1W. So here, this is a review for the chemistry unit, and we're going to go through the key parts so that the students can be prepared for their exam. So the first topic we're going to have today will be about the WHMIS pictograms. So WHMIS is the Workplace Hazardous Materials Information System. It allows scientists and also people in the workplace to document the type of chemicals they're using as well as their effect. So the first one, the one that we often see, is about flames. So anything that with a spark, bit of oxygen will burn. So this is this symbol right here. The one with an O, it's an oxidizer. That means that materials in contact with oxygen will burn and oxidize, and therefore it can be dangerous. We also have the explosives section for explosive or materials that are unstable and they can react and have an expanded volume. We have the compressed gas. So here it shows a gas cylinder. So propane gas, ethylene, oxygen that are being used in the industry and hospitals. With respect to toxic materials, we have here a skull and crossbone for acute toxicity. We have here health hazards. So here they tend to be long-term consequences like carcinogenetic work, sensitivity to respiratory system, as well as the reproductive system. We also have the exclamation point, and this one, it's a variety of toxicity with respect to human health. Indeed, irritation, skin irritation, and such. We also have corrosion, so acids and base in high concentration. We have this one here for biohazardous, for people doing research on viruses and other viruses and bacteria that are harmful for humans. And this one here, it's about the environment. Often it is for terrestrial and aquatic ecosystem that could be affected by different chemicals brought into them. This one is not necessarily recognized around the world, but this is one that we have here in Canada and in Europe, in North America. So that is amazing. When we think of pure substances in chemistry, let's see what it means. So we have two categories. We have elements and compounds. So the first one are called elements, and interestingly enough, they are organized, and I'll show you how organized they are. They are organized on the periodic table of elements. So I'm going to put here in the English version. There we go. So the periodic table of elements is organized to have all the different elements in the universe, known naturally occurring as well as synthetic ones. Perfect. So when we have elements and we are to take that elements and break it down in smaller and smaller pieces of that element, we end up with one single particle, which are called atoms. So we can have iron atoms, copper atoms, and gold atoms. When we put many atoms together, one type of substance, we end up with what we call elements. The second groups are called compounds. Compounds are made of molecules of matter, similar type of particles made of one type of matter, but they are groupings of several atoms together. Here are a few examples. First one will be water, H2O, carbon dioxide, CO2, and here we have glucose, C6H12O6. These are compounds. So if you were to take several of these molecules together, you will end up with matter that is called a compound. So this is the big difference between the two here. So very nice. So the next one we're going to talk about will be the particle theory of matter. So here there are 5 that we have for you. The first one here is all matter is made of small particles. As I mentioned, I can have a piece of aluminum that I break down in smaller pieces, all the way to one type of particle? Aluminum. If I have a glass of distilled water and I have 100 milliliter divided into for 50 ml, divided into 25 milliliter, and keep dividing the volume of water smaller and smaller and smaller, I end up with one molecule of water. Second one, every pure substances have their own types of particles. So here we have particles of water, particles of iron. Next one, all particles attract each other. So here, if you think of a metal, so here I have an aluminum pencil. This pencil is made of one type of atoms, and all of them are together as a solid. Now, if I were to increase the temperature, this aluminum will turn into a liquid, and then at several thousands degrees Celsius will end up into a gas. Next one, particles are always in movements. So if you think of a solid aluminum like this, the particles will be in movement because there's some energy in the particles. If I have ice that I warm up above 0 degrees Celsius, I have water. And if I increase the temperature above 100 degrees Celsius, I have vapor, which is a gas form of water. And water is the liquid form of ice. Now, if you were to take the temperature and bring it down in colder, 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 it gets to a point when you have the absolute zero, and it's about negative 273 degrees Celsius or so. We have 0 Kelvin, and it's a place where matter has no energy, and therefore will be all in solid form. Interesting. And the last one, in general, the more temperature you put into matter, the more the particles will move, and the more they will expand and take more space. Here's an example. I made tea this morning, and this tea here, I have lukewarm water. When I put the tea bag in the hot water, it was dissolving quite rapidly because the water molecules were moving faster. If I was to try to do a tea in cold water, it could work, but it would take a lot more time because the water particles are not moving as fast. So these are the key points about the particle theory. So let's see if we can go to the next page. When we think of matter, we have what we call physical properties, and they can be divided in two parts. The first one is what we call qualitative properties. These ones have been discussed and talked about for centuries, because these are coming from our 5 senses. So you can see different colors, you can hear different sounds when we have, for example, when you open a can of pop, you can hear the carbon dioxide coming out. We can have also the smell, the amazing scent from flowers, for example. However, qualitative properties are always about the observer's experience. So the way I see colors is different than other people seeing colors. That is in contrast with what we call quantitative data. Quantitative data is about quantities. It's about being able to use a piece of equipment to measure a property of matter, and these have units. So if you think of temperature, for example, we talked about it earlier in the particle theory. When you think of temperature in Kelvin, in degrees Celsius, in Fahrenheit, we can measure them, and we have units for them. If you have mass, you can measure in grams or kilograms. If you think of density in grams per centimeter cubes or tons per meter cubes, if you have dimensions, it could be centimeters, meters, kilometers, astronomical units. These can be measured. That's the big difference between the two. Now, we're going to go into change and chemical change. So let's see if we can go to the next step. Now that we have talked about the physical properties, let's see if we can talk about the chemical properties at this time. So when you think of chemical properties, it is the properties of different matter to react with other substances. So for example, you can have a substance that can react to water or oxygen. For example, if you think of iron that will rust, so if you have a light gray materials, iron, in contact with water and oxygen, it will rust and it will turn orange. If you have a reaction to acid, for example, if you have acid burn, you can use a TUM, which is an anti-acid, to neutralize the acidity. So that's a chemical property. You can also have combustibility. So if you have wood or fossil fuels, for example, in contact with oxygen and some heat, you can have more heat and more energy being produced. This is what we call the chemical property of matter. Now, these are properties, but when you have a reaction, so that means you put two materials together to create a new substance, we have what we call a chemical change. A chemical change is when you have a new substance being created following a reaction. So, for example, if you put together, let's say you burn wood, you have in smoke particles, but you also have water and carbon dioxide. It's a change in chemistry from wood to a gas. Sometimes you can have the creation of a solid when you have, for example, two liquids and you have a precipitate. That's an example. If there's a change in color, that shows that there's a chemical change. If there's a change in temperature, then there is also a chemical change. So if you have, let's say you participate to a volleyball tournament and you hurt your ankle, they're going to put an ice pack. So you're going to have a solid and liquid, and together, because of their chemical properties, they will create a reaction, and then the ice pack will get cooler. So what's interesting with chemical changes is that it is irreversible. So that means that we cannot go back to the original components. So for example, if you have, for example, a log in a fireplace, once the log has burned, you have ashes, but you cannot take the ashes, try to get carbon dioxide and water, and try to get the log back because it's irreversible. So chemical change is what it means. Now, it does happen that if you have, earlier we talked about physical properties. So when we have a physical property of matter and we can have physical changes, what's interesting with that is that we have reversible change. If you're, for example, we talked about water, vapor, and ice. Ice can be melted to get water. Water can be boiled to get vapor, but you can take the vapor and condense it to get water and back to ice. The properties of water, the type of matter is still water. The state may be different, but it does not change its own chemical composition. That's why when you have physical change, they are reversible. And when you have chemical changes, they are irreversible. So that is the section here about the properties and changes. So let's see what will be the next topic at this time. Let's talk about the atomic structure of the atom, a bit of history, and a bit about the Bohr-Rutherford diagrams. So first of all, if you think of atoms, they are the basic blocks of what matter is. So there's a history on how this happened. So let's see. If you look on my channel, I have a video on the history of the atom for a few thousand years. Today, we're going to work on the last 200 years. I know it's a bit Eurocentric. However, it explains well what we have so far. So here, a couple hundred years ago, we have Dalton that said that chemically, when you have different types of matter, we have different type of particles. So for example, we have a particle of gold, particle of water, particle of lime. Different particles, different matter has their own different particles here. Next one, we have Thomson. Thomson, through his study of electricity, realized that when you have a neutral particle, that one is also affected by electricity and electromagnets. So he did that particles existed, like Dalton did, but within it, we have a positive particle with little electrons, negative electrons that are sparkled on it. This idea of a chocolate chip cookie or a plum pudding. We have Rutherford, and Rutherford, his idea through his experiment with protons and gold leaves, realized that a particle has most of its mass in the nucleus in the middle, but also had electrons that are moving at the speed of light all around the nucleus, keeping in mind that we have particles from previous ideas of what matter is. Bohr was his student, and what he discovered that electrons have energy and they are found mostly in specific places around the nucleus. So he used his teacher's or his professor's structure with most of the density in the nucleus, but put layers or places where you would have shells where electrons would be here. Now we have Chadwick in the 40s or 50s, in 1940s, 1950s, when his research showed that he had the same matter, which means that some matter with the same number of protons, so the identity were the same, but had different density. So that means that he had to be able to explain that, have in its nucleus, on top of the protons, a particle that would have no charge, but would be as heavy as protons, that would affect the density of matter. So this discovery of isotopes within similar types of matter. So here at the beginning of neutrons. So here when you look at the key or the basic particles, we have protons that are positive, neutrons that are neutral, and electrons that are negative. Protons are always found in the nucleus with the neutrons, and electrons are along shells, especially for the first 20 elements on the periodic table. Now, through this history, we came up with this idea of what we call Bohr-Rutherford diagrams. So from the research from Rutherford and Bohr, and let's see what it looks like. So if you have lithium, and in a moment, we're going to look at the periodic table to see what information it shows us. Lithium has an atomic number of 3, which means it has 3 protons, an atomic mass of 7, which means that if you do 7 minus 3, you have 4 neutrons. Because it has 3 positive protons, it needs 3 negative electrons around the nucleus. So we have 1, 2, and 3. If you take fluorine, fluorine has an atomic number of 9, atomic mass of 19, therefore 9 protons here. 19 minus 9 is 10, with 10 neutrons in the nucleus. Because we have 9 protons, we also have 9 electrons, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So here is the basics for the Bohr-Rutherford diagram and the structure of matter. Perfect. Now, how do we get information such as an atomic number of 3 and an atomic mass of 7? So let's have a look at the periodic table to see if we can share information, shed light to what it is. So I'm going to go back to my periodic table. Perfect. And here we are. So when you look at the periodic table, there's a few things we need to look into. First of all, we need to see that there are rows. So we have rows and they're numbered from 1 to 7. So the rows here, so the first row is called the first period, second period, third period, fourth period, and so on. And you also have at the top here numbers, and these are group numbers. So here we have the first group, here second column, the second group, the 18th column, the 18th group. So that's something to look into. Now, if you look at calcium right here, calcium has a number 20. That's the atomic number. The atomic number is the number of protons in the nucleus, and that's the identity of an element. So, or an entity of the element and atoms of that same element. So hydrogen here has an atomic number of 1 because it has 1 proton. Helium has an atomic number of 2 because it has 2 protons. Calcium here, as mentioned earlier, has 20 and the atomic number of 20, it has 20 protons. And if you were to go to gold, gold has an atomic number of 79. So the identity of any atoms in the universe is based on the number of protons, the positive particles in the nucleus. So that's the first thing. The next one, we have what we call the atomic number right here. The atomic number is the sum of all the mass of all the isotopes of a specific element. So here, if you have, for example, 40.078, that means that most of the calcium isotopes have 40 as an atomic mass or atomic number. And we have here, is it the atomic number? It's the mass number. There you go. The mass number is the number of protons and neutrons. So here, most of them are 40. That means that 40 minus 20, most atoms of calcium have 20 neutrons. There is a number of calcium atoms that would have more than 20 neutrons. And that's why we have here an atomic mass that is a bit higher than 40. If you think of hydrogen here, hydrogen has atomic number of 1, that means 1 proton. And if you look at the atomic mass, you can round it up to 1. That means that most hydrogen atoms have no neutrons. If you go for helium, helium here has an atomic number of 2, an atomic mass of 4. That means that most of the helium atoms have 2 protons and 2 neutrons. If you look at chlorine, that's interesting. So here, to simplify it, you could see it's about, you can round it up to 35.5. So to simplify, you could say that maybe, so 35 minus 17 is 18 neutrons. So maybe half of the chlorine atoms would have 18 neutrons. But if you are saying because it's 35.5, you have chlorine at 36, that means that you have also maybe half of the chlorine atom with 19 neutrons. But I know that chlorine has 5 to 6 of maybe more isotopes. So this is what the atomic mass means. Perfect. Now, on top of that, we have some trends. So if you look at the atomic mass, it goes from 1 here all the way to 118. So that means the periodic table is organized numerically from 1 to 118. On top of that, the atomic number goes from 1 here to the left, and it increases from left to right. So here we have 3, 4, 5, 6, 7, 8, 9, and 10. And it also increases in their groups. So we have 3, 11, 19, 37, and so on. So that's a trend we can see. Another trend that is interesting will be the radius of the different atoms. So if you take the second period here, we have lithium and beryllium. We have here an atomic number of 3 protons that are positive. That means there are 3 electrons as well. So we have 2 electrons on the first layer and 1 on the second layer. So here we have beryllium, we have bore, carbon. So if you can see here, we always have 2 electrons on the first level and then 4 on the second level. And here I refer to when you have the Bohr-Rutherford diagrams where the electrons are put together. Very nice. So here what's interesting for carbon is that you have 6 protons in the nucleus. So the nucleus has more and more protons, therefore attracting electrons more and more. So when you go to nitrogen and oxygen, we have a nucleus that is always increasing in positive charges, and therefore the negative charges on the valence shell, which is the level or the shell where the outermost electrons are, they're getting tighter and tighter around the nucleus because there's more charges, more positive charges in the nucleus, attracting the electrons of the valence shell. So as we go from left to right, the radiuses are getting smaller and smaller. However, when you go from hydrogen, we have electrons on the first shell. We have lithium, 2 on the first shell, and oops, we need the second shell now. Sodium, now we have 1 on the third shell. Potassium, a 4th shell. That means that every time you go down the periodic table, you add a shell, and therefore you add in the radiuses. So radius increases from top to bottom all across the board here. So these are something to look into with the periodic table so far. Very nice. So let's see if there are any questions at this time. So I was certified for 10 years to manage and oversee transport of NH3. So this is ammoniac. And so that what state and matter it is important. That's very true. So, and since you were looking at transportation, Sijenda, you most likely had on your transport trucks different symbols, such as Wemyss symbol that showed, I'll show the here, you had symbols like this, pictograms on the trucks showing what they were. Now in 2015, we started to have those red squares like this or diamond shape. Before 2015, we had the circles like this. Now we went into this red diamond shape because in Europe and in North America, they're using these symbols. They're trying to mainstream them to make sure things work well. The only one that did not change and kept the black circle was the biohazardous materials. So here, this was before 2015 and after 2015. That's interesting. So here, when we think of chemistry, it's not just in labs, but it's in producing them, transporting them, and then using them. And all of this is important to make sure that the workers, the drivers, and the scientists and the technicians are all doing work safely. And yes, environmentally important as well. So for example, if you have ammoniac that is going in high concentration, we don't want to be in a situation where we are polluting the ecosystems either on land, and sometimes if you're using other substances in liquid form, they percolate through the soil and then it contaminates the aquifer. That is not very good for the environment. So here, we're very happy, Sijenda, that you were there to make sure that transportation was done safely for the drivers, but also everybody involved in transportation. Very nice. I do enjoy that. Perfect. So let's see what is the next thing we're going to talk about. Periodic tables, group. Okay. When we think of the periodic table, so we have to keep in mind that from the Bohr-Rutherford diagrams, if you look at this one here, we have the lithium where we have 2 electrons on the first layer and 1 on the outer layer. But what's interesting is that when you are looking at the lithium here, you have 2 on the first electron shell and then 1 on the outer shell. For sodium, you have 1 on the outer shell. Potassium, you have 1 on the outer shell. So the number of electrons on the valence shell makes a difference with respect to how they react with their environment. So what's interesting, so we have grouped together different substances with similar characteristics. So we have the alkali metals here. What's interesting with those, they tend to be solid at room temperature. They dissolve in water nicely. And when they do, they conduct electricity. They tend to have a fun cubic shape as a solid. And let's see. They tend to be, I can't think of other properties right now, but because they have similar characteristic, they react to water. That's another one. And the other one here is that they're very soft metals. There you go. They behave similarly because they have similar properties. They have similar number of electrons on their outer shell. The second family is the alkaline earth metals. So those ones are very similar in the fact that they have 2 electrons on the outer shell. And interestingly enough, it gives them similar properties. They're a bit harder than the alkali metals. They do react with water, but much less, and they are solid at room temperature indeed. Now there are other type, so here there are 2 groups of metals, and here I'm going to show the metals here. All the metals on the periodic table have the opportunity to give electrons because they are either further from the nucleus or available to share or to transfer to other atoms. So who will they transfer those electrons with? So the metal tend to share their electrons with nonmetals. So the nonmetals here are in green. We have the fluorine, chlorine, nitrogen, phosphorus, and so on. What's interesting with the nonmetals, like we have here for the fluorine, is that here we have what we call the two goals of atoms. So the two goals are the following. They want the same number of protons than electrons. So here we have these nicely. But the second goal, they want a valence shell that is full. So that means that if you have here lithium, lithium here has 2 electrons on the first outer shell, the first shell. So here it has 1 on the valence shell. If it let 1 go, then it would have a full outer shell. And that's why all the metals will go from here first. But in order to satisfy the next condition, they're willing to give their electrons. If you think of the nonmetals here, we have fluorine. We have here 7 electrons on the outer side, the outer shell. But the valence shell of fluorine can have up to 8. So that means that if it could accept 1 electron, then it would account for the second condition here. So all the nonmetals want to have electrons to complete their valence shell. So let's continue here. Very nice. So we have the nonmetals. The next one is the noble gases. The noble gases are interesting because helium, neon, argon, and so on, they all have their 2 conditions fulfilled. For all of them, they have the same number of protons and electrons, and they have their outer shell or the valence shell full. So that means that they tend to be very inert. It means they don't react with the environment very much because they are satisfied the way they are. So here we have, for example, as you go further down and to the left, we have here atoms that are very, very reactive because we have 1 electron that is available to give away. So here on the right side, the further up to the right, all the way to fluorine here, and fluorine being the more reactive, we have atoms that are aggressively looking for electrons to be happy. And another group is called the halogens. Let's see. The halogens are the second last column here with fluorine, chlorine, bromine, and iodine. So here we have these elements that they are looking for 1 extra electrons to complete their valence shell. So they all react similarly, and they have their own name and own family. So in grade 9, we're looking at the alkaline metal. The alkaline metal, alkaline earth metal. We have the nonmetals, and we have the noble gases. Within the nonmetals, we have the halogens, which are the fluorine, chlorine, bromine, and iodine. So these are the characteristic and families that are identified on the periodic table. Let's see if we can cover the last topic for today's show. So let's see. So we did look at the fact that we have lithium here, and lithium is looking for 2 goals. The first one is the same number of protons and electrons, which is satisfied here. And the second one is the full valence shell. In order to have a full valence shell, what will happen here is that the lithium, which is a metal, will give away its electrons like this. And in doing so, we have 2 electrons on the outer shell. We have a full valence shell, which is great. So you end up with an atom of lithium that is not positive. And the reason why it's positive, it has 3 positive protons and 2 negative electrons. So it has 1 more positive. When you have here an atom that is not positive, therefore it has a charge, we call it has a positive ion or cation. So new pieces of information. When you have a charged particle, a charged atom, we have what we call an ion, I-O-N. When we are, so let's see if I can move. Can I take away this? Oh, there you go. So if you think here, positive ion. When you have a positive ion, the other word is cation. So that is the word I have for that. For fluorine, what do we have? We have here the same number of protons and electrons. However, in order to have a full valence shell, it will look for an extra electrons right here. When it has an outer shell full, it's happy. However, there are one more electrons, 10 electrons compared to 9 protons. That means it has a charge and it has a negative charge. How do we call the negative charge? Negative. It is called a negative ion, and the other word that we can say, it is an anion. An ion is a negative ion, for example, F minus. It could also be chlorine like this, negative, or oxygen 2 negative like this. Perfect. So this is what we have. Now, what's interesting, we have lithium that has an electron to give away, fluorine that wants to have an electron. So there's a transfer of electrons right here. So what do we get? We get a new substance, Li, let's see, LiF like this. It's a lithium fluoride. This is what we called an ionic compound. Ionic compound like this. Why is it an ionic compound? Because it's made of a positive and negative ion. When you have an ionic compound, the relationship between the ions is called the ionic bonds or ionic bonding to make sure that they get together. So that is one piece of information. The second piece of information to look into would be when you have a fluorine that wants 1 electrons, but you put another fluorine that also wants to have an electron. So here there's something different we have to do. So first of all, they want to have the same number of protons and electrons, so they're happy. However, they also want to have a valence shell that is full. So what they will do is that they will share electrons to make sure it works well. So what do I mean by sharing? Well, this one here will say, you know what, I want an electron. It will say, share one of your electrons with me. So when it does, it now has 1, 2, 3, 4, 5, 6, 7, 8 electrons on the outer shell. However, as soon as this fluorine shared an electron, they say, wait a minute, I shared one with you. I want you to share one with me too. And therefore, this fluorine atom would share one of its atom as well. So let's see, 1, 2, 3, 4, 5, 6, 7, 8 electrons. And since the electrons are going at the speed of light, we end up with a very stable compound made of atoms that are sharing electrons. When we have atoms that are sharing electrons, we have what we call molecular compounds. Molecular compounds are compounds where atoms are sharing electrons. What is the relationship between these atoms? We call it covalent bonds or covalent bondings. Sometimes I've also, depending where you go, you can also have molecular bonds. Sometimes they interchange these words depending on the region around the world or the literature you're looking into. So I've seen in French, for example, we've seen molecular compounds, molecular bonds, and then covalent bonds and molecular bonds. I've never really heard covalent compounds, but if you said so, people would understand what you're saying. So hopefully this is a great review for those compounds.